40 kilograms of water every single second, pouring off an object that shouldn't behave this way, nearly 3 times farther from the Sun than Earth, where liquid water should barely exist at all. A visitor from another star system, older than our entire solar system, moving at impossible speeds through our cosmic neighbourhood. A trajectory so unlikely, astronomers calculated the odds at 5 in 100,000. Chemistry that broke every rule, a debate that split the scientific community in half, and a question that keeps getting louder. Is this just a comet? Or did we just witness first contact without even realising it? This is Comet Through Eye Atlas, the wanderer from the ancient galaxy. And what happened next changed everything we thought we knew. If you want to stay updated on what happens next, hit that like button and subscribe. Tell me in the comments where you're listening from, what time it is there, and whether you think this is just extreme cometary activity or something else entirely. Chapter 1. The Fire That Shouldn't Exist. The discovery came quietly, as most astronomical breakthroughs do. No fanfare, no press conference, just data streaming into computers at NASA's Neil Gehrels Swift Observatory in late July 2025. The spacecraft, designed to catch fleeting gamma-ray bursts from distant cosmic explosions, had turned its attention to something much closer to home. Something that would challenge everything we thought we understood about comets. 3I Atlas had been discovered just weeks earlier by the Asteroid Terrestrial Impact Last Alert System survey in Hawaii. Initial observations showed it was moving fast, too fast. Its trajectory marked it immediately as an intruder, an interstellar visitor passing through our solar system on a hyperbolic orbit. Unlike the elliptical paths of native comets that loop around the Sun repeatedly over centuries or millennia, a hyperbolic orbit is a one-way ticket. You come in from interstellar space, swing around the Sun once, and leave forever. This was only the 3rd confirmed interstellar object ever detected. The first, 1I Oumuamua, arrived in 2017 and sparked years of debate about whether it was a comet, an asteroid, or something else entirely. The second, 2I Borisov, appeared in 2019 and looked reassuringly comet-like, with a visible tail and spectroscopic signatures matching what we expected. Now Atlas had arrived, and within days of discovery, astronomers knew it was different. Dennis Bodowitz led the Swift observation team at Auburn University. His specialty was ultraviolet spectroscopy, the art of breaking down light from celestial objects into component wavelengths and reading the chemical signatures hidden there. When he pointed Swift at Atlas on July 28th, and again in early August, he was looking for hydroxyl emissions. Hydroxyl, the OH molecule, is what you get when sunlight tears water molecules apart. It glows at specific ultraviolet wavelengths, creating a telltale signature that reveals how much water a comet is losing. The telescope stared for hours, stacking exposure after exposure to build up enough signal. Comets are faint, especially at distance, and ultraviolet light from deep space is hard to capture. But slowly the data accumulated, and when Bodowitz ran the analysis, the numbers that came back made him check his calculations twice. 40 kilograms per second. That was the water production rate at 2.9 astronomical units from the Sun. To put that in perspective, 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. At 2.9 AU, Atlas was almost 3 times farther out than we are, receiving less than 1/9 the solar heating. At that distance, comet surfaces should be cold, barely above the point where water ice begins to sublimate. Most comets at that range are quiet, dormant, their volatiles locked away beneath frozen crusts. Yet Atlas was pouring out water as if it were much, much closer to the Sun. The measurements were published in Astrophysical Journal Letters on September 30th. The paper laid out the observations methodically, showing the ultraviolet spectra, the hydroxyl detection, the mass loss calculations. But beneath the careful scientific language was an undercurrent of puzzlement. The team had modelled what they expected to see at 2.9 AU. Typical comets at that distance show maybe 3 to 5% of their surface actively releasing gas. Atlas was showing at least 8%, nearly double the predicted activity. That discrepancy meant one of 2 things. Either their model was wrong, or something unusual was happening on Atlas that standard comet physics couldn't explain. Bodowitz and his co-author Zexi Xing from Johns Hopkins proposed a solution. The key was in what other telescopes had detected: ice debris floating in the coma itself. Not just vapour, but actual solid chunks of ice suspended in the cloud of gas and dust surrounding the nucleus. Think of it this way. When sunlight hits the surface of a comet, it warms the ice gradually. The outer layers heat up first, then slowly conduct warmth deeper. This takes time. A large solid block of ice on a comet's surface sublimates from the outside in slowly and steadily. But now imagine that block breaks apart. Maybe thermal stress cracks it, or internal gas pressure blows chunks off, or ancient fractures finally give way. Suddenly, instead of one large ice block, you have hundreds or thousands of smaller fragments scattered through the coma. Each fragment has much more surface area relative to its volume. They heat up faster, they sublimate faster. Each ice fragment becomes a tiny steam vent, contributing to the total water output. From Earth, when telescopes measure the hydroxyl glow, they can't distinguish between water coming from the nuclear surface and water coming from debris in the coma. It all adds up together. The result looks like the nucleus is far more active than it actually is. This explanation was elegant. It matched observations from near-infrared telescopes that had caught hints of crystalline ice in Atlas's coma, ice with the spectral signature of solid material, not vapour. It explained why the water production seemed so high at such a great distance, and it raised a fascinating question. Where did those ice chunks come from? Had Atlas experienced a fragmentation event before discovery, something that cracked the nucleus and sent debris into orbit around it? Comets are fragile. They're held together by gravity so weak you could escape it with a running jump. Thermal stress, internal pressure, even the gentle push of outgassing can be enough to break them apart. Perhaps Atlas had already started fracturing during its inward journey, and what we were seeing was the aftermath. Or perhaps this was just how interstellar comets behaved. Maybe objects that spent billions of years travelling through the harsh radiation environment of deep space developed different structures than solar system comets. Cosmic rays bombarding the surface, temperature swings between near absolute zero and whatever slight warmth they absorbed passing near stars, micrometeorite impacts over geological timescales. All of that could create a deeply fractured, weakened structure prone to shedding debris. There was another possibility, one that nobody put in the peer-reviewed papers but that whispered through conference hallways and late-night research group discussions. What if the ice debris wasn't accidental? What if it was engineered? The thought seemed absurd at first glance. Comets are natural objects, ancient remnants from planetary system formation. They're not spacecraft, not artifacts, not technology. But then you started adding up the anomalies, and the absurdity became harder to dismiss entirely. Atlas wasn't just releasing water at an unexpected rate. Its trajectory was statistically improbable. Its chemistry would turn out to be unlike any comet ever studied. Its brightness varied in ways that defied simple explanations, and the timing of its arrival, passing close to multiple planets in our inner solar system, seemed almost too convenient. Avi Loeb, the Harvard astrophysicist who had become famous for suggesting Oumuamua might be extraterrestrial technology, was already watching Atlas closely. He had developed what he called the Loeb scale, a rating system from 0 to 10 for assessing how likely an interstellar object was to be artificial rather than natural. 0 meant definitively natural, 10 meant definitively technological. Most objects sat at 1 or 2. In mid-August, Loeb quietly updated his assessment of Atlas from a 4 to a 6. A 6 didn't mean alien spacecraft. It meant the probability was non-negligible. It meant the object had accumulated enough anomalies that it warranted serious investigation as a potential techno-signature. It meant we couldn't simply assume it was natural and move on. The scientific community's reaction was mixed, to put it mildly. Most astronomers saw a comet behaving unusually, but still within the bounds of natural processes. The 40 kilograms per second of water loss, impressive as it sounded, wasn't impossible. The ice debris explanation made sense. Comets surprised us regularly with unexpected behaviour, but that didn't make them alien probes. Yet a small but vocal group argued that dismissing the possibility too quickly was its own form of bias. We had only detected 3 interstellar objects ever. Our sample size was laughably small. Making confident statements about what was normal or abnormal for interstellar visitors was premature. Maybe some fraction of objects passing through stellar systems were natural and some were artificial, and we simply didn't have the tools or framework to distinguish between them yet. the Swift observations were just the beginning. In the weeks that followed, telescopes around the world turned toward Atlas. The James Webb Space Telescope, NASA's newest and most powerful infrared observatory, captured detailed spectroscopy in early August. SphereX, a space-based infrared telescope, mapped the comet's carbon dioxide cloud. Ground-based observatories in Hawaii, Chile, and the Canary Islands tracked its brightness and position. Every night brought new data, new measurements, new pieces of the puzzle, and every new piece made the puzzle more complicated. The water production rate that Swift measured was supposed to be impossible at 2.9 AU, but it was happening. The ice debris field was supposed to be rare, a sign of recent fragmentation or unusual stress. But there it was, confirmed by multiple instruments. Something else bothered researchers, though it took a while before anyone said it out loud. The timing was strange. Atlas had been discovered on July 1st by the Atlas survey, but pre-discovery images went back to mid-June. Before that, nothing. The comet had approached from the direction of Sagittarius, from the galactic center, one of the brightest and most crowded regions of the sky. Detection against that background was extraordinarily difficult. It was almost as if Atlas had intentionally approached from the direction that made early detection hardest, almost as if it had timed its arrival to minimize warning. That kind of thinking felt like conspiracy theory territory. Comets don't time anything, they don't plan. They follow the laws of physics, moving along trajectories determined by gravity and initial conditions billions of years ago. Attributing intent to a comet was anthropomorphizing, projecting human agency onto mindless rock and ice. But then again, if an advanced civilization wanted to send a probe to study another star system, what approach vector would they choose? Coming from the galactic center made tactical sense. You arrive masked by background stars, giving the inhabitants minimal time to prepare or respond. By the time they detect you, you're already deep in their system. Was that what happened? Was Atlas reconnaissance? Had some ancient civilization, perhaps long extinct, sent probes out into the galaxy millions or billions of years ago, and we just happened to be in the path of one? Or was this just pattern-seeking, the human tendency to find meaning in randomness, to see faces in clouds and agency in coincidence? The data from Swift couldn't answer those questions. All it could do was document what was happening. Water loss at rates that shouldn't occur at that distance. A comet behaving in ways that challenged models built on centuries of observation. An object that demanded explanation, even if the explanations felt inadequate. As August turned to September, Atlas continued its inward journey. The water production should have increased as it got closer to the Sun, as solar heating intensified and more ice sublimated. Astronomers prepared their telescopes, allocated observation time, coordinated international campaigns to track every aspect of the comet's evolution. But there was a problem on the horizon, a gap in coverage that nobody could avoid. Atlas was heading towards solar conjunction. In late October, it would pass behind the Sun from Earth's perspective, disappearing into the solar glare. For approximately 6 weeks, from early October through mid-November, ground-based telescopes would be blind. The comet would be too close to the Sun in the sky to observe safely. Even space-based telescopes had strict solar exclusion zones to protect their delicate instruments. And the most critical moment, perihelion, when Atlas would make its closest approach to the Sun and experience maximum heating, would happen right in the middle of that blackout. October 29th, at a distance of 1.36 astronomical units, completely hidden from view. Whatever happened during that hidden perihelion passage would occur without witnesses. The comet would emerge in November changed, and we would only infer what had happened from the aftermath. The fire that shouldn't exist was just the opening act. The real story was still ahead, hidden in the solar glare, waiting to be revealed. If it emerged at all. Chapter 2. 10 billion years in the dark. 10 billion years is an almost incomprehensible span of time. When this object first formed, our Sun did not exist. Earth was not even a possibility, just scattered atoms drifting in some long-vanished molecular cloud. The universe itself was less than 4 billion years old, still young and wild, with star formation rates far higher than today. Somewhere in the thick disk of the Milky Way, in a protoplanetary disk circling an ancient star, ice and dust began to clump together. The process was the same one that has built countless worlds throughout cosmic history. Gravity pulled particles together, Collisions stuck them into larger aggregates. Over millions of years, those aggregates grew into planetesimals, the building blocks of planets and moons and comets. Most planetesimals stayed where they formed, eventually becoming part of planets, or remaining in stable orbits as asteroids and comets. But some got ejected. Gravitational encounters with forming gas giants could fling smaller objects outward at high speed. A close pass by a massive planet was like a gravitational slingshot, accelerating the planetesimal beyond the escape velocity of its parent star system. Atlas was one of those unlucky objects, or perhaps lucky, depending on perspective. It was thrown out into interstellar space, leaving behind the star system where it formed, beginning a journey that would span the age of the galaxy. The trajectory analysis came from Javier Sanz Pérez Cuevas and his team at the University of La Coruña in Spain. They used data from the Gaia Space Telescope, which has been mapping the positions and velocities of more than 1 billion stars in our galaxy. By tracking how stars move through space, Gaia allows astronomers to rewind time, calculating where stars were in the past and where they will be in the future. Pérez Cuevas ran Atlas's trajectory backward through 10 million years of orbital integration. The goal was to find close encounters with stars that might have perturbed the comet's path, deflecting it toward our solar system. If you could identify which star Atlas passed near, you might trace it back to its origin system. The team identified 93 potential stellar encounters. 62 were classified as high confidence, meaning the uncertainties in position and velocity were small enough to trust the calculations. These were stars that Atlas should have passed within a few light years of, close enough that their gravity might have bent the comet's trajectory. But here was the strange part. None of them did. Atlas emerged from 10 million years of travel essentially unperturbed. Its path through crowded stellar neighborhoods, through spiral arms where stars clustered densely, through regions where gravitational interactions should be common, left almost no mark on its trajectory. The reason was velocity. Atlas was moving at 58 kilometers per second relative to the local standard of rest, the average motion of stars in our galactic neighborhood. That is fast, too fast for most stellar encounters to have much effect. Think of it like a speeding bullet passing through a room. If you throw a baseball at the bullet, you will not deflect it much. The bullet's momentum is too great. You need something massive moving fast to significantly change the bullet's path. Similarly, a comet moving at 58 kilometers per second needs a very close encounter with a very massive star to have its trajectory altered noticeably. Most stars Atlas passed were not massive enough, or not close enough. It just flew by them, gravity tugging slightly but not enough to bend the path in any meaningful way. The comet was like a ghost, drifting through the galaxy without being caught by any of the gravitational wells it encountered. That high velocity also told researchers something important about Atlas's origins. Our Sun orbits the galactic center at roughly 220 kilometers per second. Most stars in the thin disk, the flat spiral structure where we live, move at similar speeds. Their velocities are all aligned in roughly the same direction, everyone participating in the orderly rotation of the disk. Atlas was not participating. Its velocity vector was tilted, cutting across the rotation at a steep angle. This suggested it came from a different stellar population. The thick disk was the obvious candidate. This is an older structure, sandwiched around the thin disk but puffed up above and below it. Thick disk stars formed early in the galaxy's history, 8 to 10 billion years ago, when the Milky Way was smaller and more chaotic. They move differently than thin disk stars, with higher velocities perpendicular to the galactic plane. They bob up and down through the disk rather than staying confined to it. Matthew Hopkins and colleagues at the University of Oxford ran population simulations. They modelled the distribution of stars in different galactic components and calculated where an object with Atlas's velocity characteristics most likely originated. The answer came back with 2/3 probability: thick disk. Not certainty, but strong likelihood. Atlas was almost certainly a refugee from the ancient galaxy, a comet that formed when the Milky Way was young and has been wandering ever since. 10 billion years of wandering. Try to grasp that timescale. Human civilization is roughly 10,000 years old. Anatomically modern humans have existed for perhaps 300,000 years. The dinosaurs went extinct 66 million years ago. Earth itself formed 4.6 billion years ago. Atlas is more than twice as old as our entire planet. It formed when the universe looked fundamentally different, when star formation was more vigorous, when the galaxy was still assembling itself, when the thin disk we live in did not yet exist in its current form. For all those billions of years, Atlas travelled through interstellar space. The galaxy is not empty. Between the stars there is gas and dust, thin but present. There are cosmic rays, high-energy particles accelerated by supernova explosions and active galactic nuclei. There is starlight, faint but pervasive. All of these things interact with a comet drifting through the void. Cosmic rays are particularly important. These are not rays at all, but atomic nuclei, mostly protons, moving at close to the speed of light. When they strike matter, they deliver tremendous energy. Individual atoms get knocked out of molecular structures, chemical bonds break. Over time, the surface of an interstellar object gets processed by this radiation, altered in ways that objects inside solar systems, shielded by stellar winds and magnetic fields, do not experience. The effects accumulate slowly but relentlessly. Crystalline ice becomes amorphous as radiation disrupts the orderly arrangement of water molecules. Organic molecules break apart or rearrange into different forms. The surface darkens as radiation creates complex carbon compounds. Volatile ices like carbon monoxide and methane, which sublimate at very low temperatures, gradually leak away even in the cold of interstellar space. But cosmic rays can only penetrate so far. A typical high-energy proton stops after travelling a few meters through ice. That means the surface gets heavily processed, but the interior remains pristine, protected by the overlying layers. A 5-kilometer nucleus has plenty of shielding depth. Whatever ice exists more than a few meters below the surface has been sitting there unchanged since the day Atlas formed. That interior is what makes Atlas scientifically priceless. It is a time capsule, preserving the chemistry of a protoplanetary disk that condensed 10 billion years ago. Everything we know about that era comes from indirect observations. We study ancient stars and measure their chemical compositions, inferring what the interstellar medium was like when they formed. We observe distant galaxies billions of light years away, seeing them as they looked in the early universe. We run computer simulations of galaxy formation that reproduce observed structures but involve enormous uncertainties. Atlas is different. It is a physical sample we can analyze directly, or at least we can point telescopes at it, measure its spectral signatures, and infer what molecules and elements it contains. That is not as good as having it in a laboratory, but it is vastly better than having nothing. The chemical signatures Atlas carries are clues to conditions in its birth system. The ratio of isotopes, for instance. Different isotopes of elements form in different nuclear processes. The ratio of carbon-12 to carbon-13 depends on how much material has been cycled through stars and enriched by nucleosynthesis. Thick disk stars tend to have lower metallicity than thin disk stars because they formed from less processed gas. If Atlas has isotope ratios different from solar system comets, that tells us about the chemical evolution of the galaxy. It gives us a data point for calibrating models of how elements are created and distributed. The ratio of volatiles, things like water, carbon dioxide, carbon monoxide, ammonia, tells us about temperature gradients in the protoplanetary disk where Atlas formed. Different molecules condense at different temperatures. Water ice forms closer to the star, where temperatures are warmer. Carbon dioxide ice forms farther out. Carbon monoxide, which stays gaseous until temperatures drop below about 60 Kelvin, forms only in the coldest outer regions. If a comet has lots of carbon monoxide, it probably formed far from its parent star. If it has mostly water with little carbon monoxide, it formed closer in. The JWST observations that would come later would reveal Atlas had an unusual chemistry, but even before those results, astronomers knew that analysing this object would teach them about planetary system formation in the early galaxy. There was also the question of what Atlas had encountered during its long journey. The galaxy is vast and space is mostly empty, but 10 billion years is a long time. How many star systems had Atlas passed through? How many times had it sailed within a few light years of another sun, perhaps one with planets, perhaps even one with life? The numbers were staggering. If Atlas has been travelling for 10 billion years at an average speed of 58 kilometers per second, accounting for the fact that its speed changes slightly due to gravitational interactions, it has covered roughly 18 billion kilometers. That is about 200,000 light-years of total distance travelled, though much of that was looping up and down through the galactic disk, rather than moving in a straight line. During that journey, it has passed within a few light years of thousands, maybe millions of stars. Some of those stars had planets. The mathematics of planetary system formation are universal. Wherever stars form from collapsing gas clouds, planets form too. Some of those planets may have had life. We do not know how common life is in the universe, but we do know the ingredients are everywhere. Organic molecules form readily in space. Water is abundant. Energy sources, whether from starlight or geothermal heat, are common. If life arises easily where conditions are right, then Atlas has passed countless worlds where life existed. And if intelligent civilizations arose on any of those worlds, they might have noticed Atlas passing through their system. They might have sent spacecraft to study it just as we are doing now. They might have taken samples, left instruments, or even used Atlas as a relay station for interstellar communication. This idea sounds like science fiction, but it is not unreasonable. If civilizations exist and last for long periods, if they send out probes or instruments that operate for thousands or millions of years, then old interstellar objects like Atlas become potential archaeological sites. Not sites where ancient people lived, but sites where ancient technologies might have left traces. Avi Loeb has made this argument repeatedly. He points out that if other civilizations exist, they might send physical probes just as we have sent Voyager and Pioneer into interstellar space. Interstellar objects passing through our solar system are the most likely places we would encounter such probes. But the possibility cannot be dismissed entirely, especially for an object as old as Atlas. 10 billion years is enough time for entire civilizations to rise and fade into extinction. If Atlas carries any markers from previous encounters, we would need to look carefully to find them. The trajectory that brought Atlas to us is remarkable. After billions of years of wandering, it arrived here, at precisely this moment when we have the technology to detect and study it. The timing is coincidence. Atlas does not care about human civilization. Its arrival is simply the result of 10 billion years of motion accumulating into a path that intersected our orbit. Yet it is hard not to feel awe. This object is older than our world. It carries ice from when the universe was young. It has travelled farther than any human artifact ever will, and for a few brief months it passed close enough for us to see it, to measure it, to wonder about the journey that brought it here. Chapter 3. The Impossible Chemistry. August 6, 2025. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its instruments toward Atlas. JWST orbits the Sun at a point called L2, about 1.5 million kilometers from Earth, positioned so that Earth, Moon, and Sun are all in the same direction. This allows the telescope's massive sunshield to block their light and heat, keeping the infrared detectors cold enough to see faint thermal emissions from distant objects. The near-spec instrument, the near-infrared spectrograph, captured light from Atlas across wavelengths from 0.6 to 5.3 micrometers. This is the infrared region just beyond what human eyes can see, where molecules produce distinctive absorption and emission features. Different molecules absorb different wavelengths, creating spectral fingerprints that allow astronomers to identify what chemicals are present in a comet's coma. What came back was a spectrum unlike anything in the existing catalogue of cometary observations. Martin Cordner from NASA Goddard Space Flight Center led the analysis team. The paper appeared on the Arxiv preprint server in late August, before formal peer review, but available for the scientific community to examine. The abstract was careful and measured, as scientific abstracts must be, but the data inside told a story that challenged fundamental assumptions about comet composition. The carbon dioxide to water ratio was 8:1. For every water molecule detected in Atlas's coma, there were 8 carbon dioxide molecules. To understand why this matters, you need context. Comets are sometimes called dirty snowballs, though that description is somewhat misleading. They are mixtures of ice and dust, with the ice containing various frozen gases. Water ice is usually the dominant component, making up 50 to 80% of the volatile material. Carbon dioxide is common, but typically much less abundant, maybe 10 to 30%. Other volatiles like carbon monoxide, methane, and ammonia appear in smaller quantities. The ratio between carbon dioxide and water varies from comet to comet, but there are patterns. Most solar system comets, whether they come from the Kuiper belt beyond Neptune or the Oort cloud far beyond that, show carbon dioxide to water ratios between about 0.2 and 3, That means water is equal to or more abundant than carbon dioxide. 3 to 1 is considered high. Only a handful of comets have ratios that elevated, and they are treated as unusual cases, outliers that require special explanation. Atlas was 8 to 1, not 3 to 1. 8 to 1. In statistical terms, this was 4.5 standard deviations above the trend line for long-period comets at similar distances from the Sun, 4.5 sigma. In science, anything beyond 3 sigma is considered rare. 5 sigma is the threshold for claiming a discovery, for saying something is definitely real and not just a statistical fluke. Atlas sat at 4.5 sigma, right on the edge of being statistically impossible. The observations showed other things too. Water was definitely present, with clear spectral features at 2.7 micrometers. Carbon monoxide appeared in the spectrum, though in smaller quantities than carbon dioxide. There were tentative detections of carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur. Water ice, not just water vapor, showed up in the near-infrared, confirming the presence of solid ice particles in the coma. Dust was visible through its scattering of sunlight. The coma showed enhanced brightness on the sunward side, exactly as expected from a comet heated by solar radiation. The outgassing was asymmetric, stronger in some directions than others, suggesting that activity was concentrated in specific regions on the nucleus rather than being uniform across the entire surface. All of this was normal. All of this matched expectations for how comets behave. The asymmetry, the dust, the water ice, even the presence of carbon monoxide and carbonyl sulfide, none of it was surprising. But that ratio, 8 to 1, that was the anomaly that demanded explanation. There were 2 main possibilities, though neither was entirely satisfying. The first involved radiation processing. Atlas had spent billions of years in interstellar space, bombarded by cosmic rays and exposed to ultraviolet starlight. That radiation could preferentially destroy water molecules while leaving carbon dioxide intact. Water is more fragile than carbon dioxide when hit by high-energy particles. The hydrogen-oxygen bonds in water break more easily than the carbon-oxygen bonds in carbon dioxide. When cosmic rays strike water ice, they can knock hydrogen atoms free. Hydrogen is so light that it escapes into space rather than recombining. Over billions of years, this process could deplete the water content of a comet's surface, while leaving carbon dioxide relatively unchanged. The freed oxygen atoms could react with carbon to create more carbon dioxide, further shifting the ratio. But there were problems with this explanation. The radiation processing only affects the surface layers. Cosmic rays penetrate a few meters at most. Below that depth, the ice remains pristine, unaffected by radiation. When a comet becomes active and starts outgassing, it sheds surface layers, exposing deeper material that should have the original composition. If Atlas started with a normal water to carbon dioxide ratio and radiation processing altered the surface, then as the surface eroded, the ratio should shift back toward normal. You would expect to see the composition change over time as fresh ice gets exposed. The observations showed no such change. The ratio measured by JWST in early August was consistent with earlier measurements from other telescopes. The composition appeared stable, not evolving as you would expect if surface processing was the dominant factor. The second explanation involved where and how Atlas formed. Different volatiles condense at different temperatures in a protoplanetary disk. Close to the star, where temperatures are relatively warm, only high-temperature materials condense. Water ice can exist at temperatures up to about 270 Kelvin. Carbon dioxide needs colder conditions, condensing at around 150 Kelvin or below. In a typical protoplanetary disk, there are ice lines marking the boundaries where different molecules transition from gas to solid. Inside the water ice line, water remains vapor. Outside that line, it freezes. The carbon dioxide ice line sits farther out in colder regions. If Atlas formed beyond the carbon dioxide ice line, in a region where carbon dioxide was abundant but water was scarce, it could naturally incorporate more carbon dioxide than water. The ratio would be locked in from formation, a reflection of the local conditions in that ancient protoplanetary disk. But achieving an 8 to 1 ratio required very specific conditions. You needed a disk with unusually high carbon abundance relative to oxygen, or you needed the comet to form in a particular temperature zone, where carbon dioxide was plentiful and water was depleted. Both scenarios were possible but not common. Stellar composition varies. Some stars have more carbon relative to oxygen than our Sun does. If Atlas formed around such a star, the protoplanetary disk would naturally have higher carbon content. That could explain the carbon dioxide dominance. The thick disk origin supported this possibility. Older stars formed from less processed gas that had been cycled through fewer generations of stars. The chemical composition of thick disk stars is different from thin disk stars, with different ratios of elements produced by different nuclear processes. The carbon isotope ratios offered another clue. JWST detected both carbon-12 and carbon-13 in the Comet emissions. The ratio between these two isotopes fell within the range found in the solar system, and in many other stellar systems astronomers have studied. That suggested the carbon in Atlas formed in a stellar environment similar to our own, not drastically different. The processes that created this carbon were familiar, even if the overall chemistry was unusual. This ruled out some exotic possibilities. Atlas did not come from a population 3 star, the very first generation of stars that formed before any heavy elements existed. It did not come from a carbon star, an evolved giant star that dredges up carbon from its interior and enriches its atmosphere. The carbon was normal, just more abundant relative to oxygen and hydrogen. The SphereX observations from mid-August provided supporting evidence. This space-based infrared telescope mapped Atlas's carbon dioxide cloud and found it extending at least 348,000 kilometers from the nucleus. That is roughly the distance from Earth to the Moon. A vast cloud of gas expanding outward at hundreds of meters per second, pushed by the pressure of sunlight and the comet's own outgassing. Water was harder to detect for SphereX. The telescope's design optimized it for certain wavelengths, and water's strongest emission lines fell outside that range. The upper limit on water production was about 4.5 kilograms per second, much lower than what Swift had measured. This discrepancy highlighted how difficult it is to measure comet composition accurately. Different instruments see different things. Swift detected hydroxyl in ultraviolet light and inferred water production from that. SphereX looked for water emission directly in infrared and came up empty. JWST found water, but also found carbon dioxide dominating the spectrum. Reconciling these observations required modelling how molecules behave in the coma. Water molecules released from the nucleus can be destroyed by sunlight through a process called photodissociation. Ultraviolet photons break water apart into hydrogen and hydroxyl. The hydroxyl then glows at ultraviolet wavelengths, which is what Swift detected. But not all water molecules get broken down immediately. Some survive long enough to emit in the infrared, which is what JWST detected. The amount you see depends on how far from the nucleus you're looking, how intense the sunlight is, and how fast the molecules are moving. Carbon dioxide behaves differently. It also gets broken down by sunlight, but the fragments are carbon monoxide and atomic oxygen. The emission patterns are different, appearing at different wavelengths. Disentangling all of this, figuring out the actual production rates and the actual ratio, required detailed models and careful analysis. The 8:1 ratio from JWST was the most reliable number because JWST observed multiple molecular species simultaneously with high spectral resolution. One detail in the JWST data stood out to researchers examining it closely. The water emission at 2.7 micrometers was not uniform across the coma. It showed structure, bright regions and dim regions, suggesting that water was coming from localized sources rather than being evenly distributed. This could mean several things. Perhaps the nucleus had active jets, concentrated vents where gas was escaping more vigorously. Comets often develop jets as sunlight heats specific areas on the rotating nucleus. If the surface composition varies, with some regions richer in water ice than others, you would see patchy emission patterns. Or perhaps the water was coming from ice debris in the coma, the same chunks that other observations had suggested were present. If those fragments had different compositions, some richer in water and others richer in carbon dioxide, the spatial distribution of emissions would naturally show structure. The carbon dioxide emission at 4.3 micrometers was smoother, more evenly distributed. This suggested that carbon dioxide was sublimating from the entire sunward hemisphere rather than from discrete jets. That fit with carbon dioxide having a lower sublimation temperature than water. At the temperatures Atlas was experiencing, carbon dioxide would sublimate readily from any surface exposed to sunlight. Water required more heating and might only sublimate effectively from specific regions. The carbonyl sulfide detection, tentative though it was, added another piece to the puzzle. This molecule is not common in solar system comets. It appears occasionally, but usually in small quantities. Carbonyl sulfide requires sulfur, and sulfur chemistry in protoplanetary disks depends on temperature and the availability of sulfur-bearing materials. If Atlas had measurable carbonyl sulfide, it indicated that sulfur was present in the formation environment. Combined with the carbon dioxide dominance, this painted a picture of a star system with unusual volatile chemistry. High carbon, significant sulfur, and relatively low water. Not the composition we see in our own solar system, where water is abundant and carbon dioxide is secondary. What would a planetary system like that look like? If water was scarce throughout the protoplanetary disk, any planets that formed would be dry worlds. Rocky planets would have thin atmospheres rich in carbon dioxide but poor in water vapour. There would be no oceans, no lakes, no water cycle driving weather and climate. Life as we understand it requires water, not just as a component but as the medium where biochemistry happens. Without water, those processes become much more difficult, perhaps impossible. This was speculative, of course. One comet's composition does not tell you everything about its parent system. Still, the chemistry was a clue, a data point constraining what that ancient star system was like 10 billion years ago. The JWST observations ended in August. The comet had moved too close to the Sun for the telescope to observe safely. Once Atlas entered that exclusion zone, JWST moved on to other targets. There were no plans for follow-up observations after perihelion. Telescope time is precious, allocated months or years in advance. By the time additional observations could be scheduled, Atlas would be fading, moving away from the Sun. The August data was likely the only detailed chemical snapshot JWST would capture. Those spectra, showing the 8:1 ratio in the spatial structure, would be the reference point for understanding what Atlas was made of, and that ratio, impossible as it seemed, was locked into the scientific record. A chemical signature from an alien star system, preserved in ice for 10 billion years, now documented and measured. The chemistry had broken the rules. What happened next would determine whether anything else about Atlas broke them too. Chapter 4. The 0 point. 0.005% question. 5 in 100,000. Those were the odds that a randomly entering interstellar object would pass as close as Atlas did to Venus, Mars and Jupiter. Not just passing near one planet, but threading through the inner solar system in a way that brought it within reasonable proximity to 3 major worlds. 0.005% probability. Unlikely? Absolutely. Impossible? No. But uncomfortable enough that it demanded attention. Avi Loeb had been calculating probabilities like this since Oumuamua passed through in 2017. That first interstellar visitor had sparked his interest not just in the objects themselves, but in the question of how to assess whether they might be artificial. Not assuming they were artificial, not jumping to conclusions, but developing rigorous methods for evaluating the possibility. The Loeb scale emerged from that work, a rating system from 0 to 10, where 0 meant definitively natural, and 10 meant definitively technological. Most objects sat at 1 or 2, showing no unusual characteristics beyond the fact that they were interstellar visitors. Oumuamua, with its cigar shape and slight acceleration that could not be fully explained by outgassing, had earned a 4 on Loeb's scale. Not proof of anything, just enough anomalies to warrant continued investigation. Borisov, the second interstellar object, was a solid one. It looked like a comet, acted like a comet, showed all the expected spectroscopic signatures. Nothing about it suggested anything other than natural origin. Atlas started at 4 when it was first discovered. Then, as more observations came in, as the trajectory became better constrained, as the chemistry revealed itself, Loeb quietly updated his assessment to 6. A 6 on the Loeb scale meant something specific. It meant the cumulative weight of anomalies had crossed a threshold where natural explanations, while still possible, were becoming strained. It meant the probability of technological origin, while still low, was non-negligible. It meant this object deserved serious investigation with the explicit question in mind: could this be artificial? The trajectory was the first major anomaly. Loeb and his collaborators had calculated the orbital mechanics carefully. An interstellar object enters the solar system on a hyperbolic trajectory, its path determined by its incoming velocity and the Sun's gravity. Once inside the Sun's gravitational influence, the trajectory bends but remains predictable. Where that trajectory goes depends entirely on the incoming vector. Most interstellar objects would pass through the solar system without coming particularly close to any planet. The solar system is mostly empty space. The planets occupy tiny fractions of the volume. For an object to pass near multiple planets requires the incoming trajectory to be aligned very specifically. Atlas came from the direction of Sagittarius, from the galactic center region. That trajectory brought it within Venus's orbit on one side, swept it past Mars at 30 million kilometers on October 3rd, and would eventually take it past Jupiter's orbit on the outbound leg in 2026. Each close approach had a probability associated with it. Venus approaches were not uncommon for objects with certain trajectory parameters. Mars approaches were less likely. Jupiter approaches for objects also passing near the inner planets narrowed the probability cone significantly. When you multiplied all these probabilities together, accounting for the specific distances and timing, you got 0.005%. Critics argued this was cherry-picking. If you look at any trajectory closely enough, you can find something unlikely about it. The fact that Atlas passed near 3 planets was notable, but someone would eventually pass near multiple planets just by chance. With only 3 interstellar objects detected so far, the sample size was too small to draw meaningful statistical conclusions. Loeb acknowledged the criticism, but pointed out that probability is exactly what you use when sample sizes are small. You cannot wait for hundreds of examples before asking whether something unusual is happening. You have to work with what you have, assess the likelihood, and adjust your conclusions as more data arrives. The timing added another layer. Atlas would reach perihelion, its closest approach to the Sun, on October 29th. That date placed perihelion in solar conjunction, with Earth and the Comet on opposite sides of the Sun. Ground-based telescopes would be blind during the most critical phase. If you wanted to perform a propulsive maneuver without being observed, perihelion during solar conjunction would be the optimal time. You're moving fastest relative to the Sun, so any thrust you apply produces maximum change in velocity. This is called the Oberth effect, a fundamental principle of orbital mechanics that spacecraft engineers use constantly. A burn at perihelion is far more efficient than the same burn at aphelion, the farthest point from the Sun. The closer you are to a massive body when you fire your engines, the more you amplify the effect. For Atlas, perihelion at 1.36 astronomical units meant that any propulsive maneuver would achieve maximum efficiency at precisely the moment when Earth-based observation was impossible. Loeb calculated the delta-v requirements for various scenarios. Delta-v is the change in velocity, measured in meters per second, that a spacecraft needs to achieve a particular maneuver. Reaching orbit around a planet, transferring between orbits, landing on a surface, all of these require specific amounts of delta-v. For a small probe released from Atlas at perihelion, the delta-v needed to insert into Earth orbit was surprisingly modest. Using a reverse Oberth maneuver, where you fire engines to slow down rather than speed up, a probe with a chemical propulsion system could achieve Earth orbit with about 500 meters per second of delta-v. That number mattered because it determined how much fuel the probe would need. Chemical rockets have what is called specific impulse, a measure of efficiency. A typical chemical rocket has a specific impulse around 300 seconds. Using the rocket equation, you can calculate that a 10-kilogram probe would need about 3 kilograms of propellant to achieve 500 meters per second of delta-v. 3 kilograms of fuel for a 10-kilogram probe is reasonable. It is within the realm of what an advanced civilization could engineer. The probe would be mostly payload, with enough propulsion to reach its target and enough power and communication systems to operate once there. The arrival window would be late November, between the 21st and December 5th, depending on exact release point and trajectory. That assumed the probe released at perihelion on October 29th performed its reverse Oberth maneuver immediately and coasted inward on a trajectory that intersected Earth's orbit. Loeb made these calculations public. He published them in preprints, discussed them in interviews, presented them at conferences. The reaction was mixed. Some astronomers found the analysis interesting, a useful exercise in thinking through what technosignatures might look like. Even if Atlas was natural, developing methods for identifying artificial objects was valuable. We would need those methods eventually, whether for the 4th interstellar visitor or the 100th. Others found it frustrating, a distraction from real science. The calculations were correct, The physics was sound, but the premise was speculative, without evidence that probes had actually been released. Discussing arrival windows and delta V requirements felt like building elaborate castles in the air. The size discrepancy became another point of debate. Early brightness measurements, taken when Atlas was still faint and distant, suggested a nucleus about 20 kilometers across if you assume typical asteroid albedo. That is absurdly large for an interstellar object. Oumuamua was a few hundred meters. Borisov was under a kilometer. A 20-kilometer comet entering from interstellar space would be a statistical nightmare, an event that should not happen in a human lifetime. But then Hubble resolved the nucleus more clearly. The Space Telescope's sharp imaging separated the nucleus from the surrounding coma and dust. The revised size estimate dropped to 5 or 6 kilometers based on the actual brightness of the nucleus itself versus the total system brightness. 5 to 6 kilometers was still large but within possibility. It made Atlas unusual but not absurdly so. The early measurements were not wrong, just preliminary, based on incomplete data when the comet was too faint for detailed analysis. Loeb pointed out that the brightness discrepancy could be explained by surface reflectivity. If the nucleus had unusual composition, perhaps with metallic components or ice with unexpectedly high reflectivity, due to its unique formation conditions, it would appear brighter than a typical comet at similar distance. That would make it look larger in early observations before better data refined the estimate. Metallic asteroids exist in our solar system. They are thought to be the exposed cores of larger bodies that got shattered by collisions, leaving behind the dense, metal-rich interiors. If Atlas had similar properties, if it was not a typical icy comet but something with different composition, the brightness and reflectivity could be unusual. That reasoning was plausible but speculative. Nothing in the spectroscopic data suggested metal. The observations showed ice, dust, volatiles, all the things you expect from a comet. If metal was present, it was not dominating the spectrum. The dust configuration added another anomaly to the list. Hubble images showed dust concentrated on the sunward side of the nucleus. That is somewhat unusual. Typical cometary outgassing produces jets perpendicular to the surface, determined by where sunlight heats the ice most strongly. Those jets can point in various directions depending on the rotation axis and the distribution of active regions. Sustained sunward dust ejection required either a very specific rotation pole orientation or some other mechanism. Loeb suggested it could be debris from impact erosion. If Atlas had been travelling at 60 to 70 kilometers per second for billions of years, impacts with interstellar hydrogen atoms would release energy. Each individual impact was tiny, but accumulate billions of them and you start eroding the leading surface. The dust we observed could be material continuously stripped off by ram pressure, like ablation on a spacecraft entering an atmosphere. That was a natural explanation, but it also happened to match what you might expect from venting or attitude control thrusters on an artificial object. The ambiguity was maddening. Every observation could be interpreted multiple ways. The rotation period was 16.16 hours, too slow to be spinning up from a symmetric outgassing, too fast to be tidally locked to anything. For a loosely bound rubble pile held together by weak gravity, 16 hours was stable and unremarkable. For a solid object, natural or manufactured, 16 hours was equally unremarkable. The rotation told us almost nothing about whether Atlas was a comet or something else. The approach angle bothered people more than they wanted to admit. Coming from Sagittarius meant approaching from the galactic center, the brightest and most star-dense region of the sky. Detection against that background was extraordinarily difficult. Atlas was discovered on July 1st, but pre-discovery images only went back to mid-June. A few weeks earlier, at magnitude 20 or fainter, it would have been invisible to surveys. If you were planning a reconnaissance mission to an alien solar system, approaching from the galactic center made tactical sense. You arrive masked by background stars, minimizing detection time. By the time the inhabitants spot you, you're already deep in their system, too late for meaningful response. That logic assumed intent, assumed planning, assumed an intelligence guiding the trajectory. For a natural comet, the approach direction was random, determined by wherever it happened to be ejected from its parent system billions of years ago, and whatever gravitational perturbations it experienced during its journey. Retrofitting intent onto geometry was dangerous. Any approach direction could be spun as strategically optimal for some reason. From Ursa Major, high galactic latitude, avoiding the plane where detection assets are concentrated. From Orion, rich star-forming region, blending in with nebulosity. The logic became unfalsifiable, which meant it stopped being useful. The early spectroscopic confusion added fuel to the debate. Multiple teams in July and early August reported difficulty identifying clear cometary signatures. The spectrum looked reddish from dust, but molecular lines were weak or absent. Water was hard to detect. Carbon dioxide was not immediately obvious. Loeb argued this was significant. A comet should show standard volatile signatures. The initial ambiguity suggested Atlas was not behaving typically. Then, as better instruments obtained longer exposures, the signatures appeared. Water, carbon dioxide, carbon monoxide all showed up. The scientific consensus was that early observations were too marginal. The comet was faint, integration times were short, signal to noise was poor. As Atlas brightened and better telescopes locked on, the data improved. What looked like an absence of volatiles was really an absence of sufficient sensitivity. That was the boring answer. It was probably correct, but probably carried uncertainty. The mothership hypothesis was elegantly simple. You do not send one probe to one star. That is inefficient. Instead, you send motherships on long trajectories between interesting systems. Each carries dozens or hundreds of smaller probes. As the mothership passes through a system, it releases probes tailored to study specific planets. The probes are expendable, small, cheap to manufacture. They complete observations and either transmit data back or store it for retrieval. The mothership continues to the next star, mapping the galaxy over millions of years. From the launching civilization's perspective, the return on investment is enormous. One mothership surveys thousands of systems, and from the surveyed civilization's perspective, the mothership is nearly invisible. It looks like a comet until it starts releasing probes. By then, it might be too late. The probes are in flight, and even if detected, interception is difficult with current technology. Loeb proposed specific tests. The Galileo project would monitor the sky during November-December when probes might arrive. 3 observatory sites with continuous coverage, optical, infrared, and radio surveys. Any anomalous object appearing in Earth orbit would be flagged. The criteria were strict. No launch history, no catalogue entry, motion inconsistent with debris, possible signs of maneuvering. The probability of detection was low, maybe 10% if probes were actually deployed, but 10% was better than 0. The counter-argument was straightforward. Extraordinary claims require extraordinary evidence. The trajectory probability, while low, was not impossibly low. Perihelion timing during solar conjunction was coincidence. The brightness anomaly resolved with better data. The dust configuration had natural explanations. Every anomaly Loeb cited had alternatives not requiring technology. And absent definitive proof, parsimony suggested the simpler explanation. Atlas was a comet. But that 0.005% probability lingered. 5 in 100,000. Low odds, but not impossible. As Atlas moved toward its hidden perihelion, the question remained unanswered, suspended between natural and artificial, waiting for whatever would emerge. Chapter 5, Red Planet Rendezvous, October 3, 2025. While Earth-based telescopes struggled with Atlas's position near the Sun, 5 spacecraft orbiting Mars had a perfect view. The geometry was favourable, the distance manageable at 30 million kilometres, and the orbiters had time allocated in their schedules to pivot their instruments skyward. This was an opportunity that would not repeat. Mars and Atlas were converging, their orbits bringing them to this close approach that had been predictable for months. Mission planners at ESA and NASA had coordinated observation campaigns, ensuring that cameras and spectrometers would capture as much data as possible during the brief window. The European Space Agency's ExoMars Trace Gas Orbiter got the best images. Its CASIS instrument, the Colour and Stereo Surface Imaging System, was designed to photograph Martian geology from orbit. Pointing it at a comet was unusual but within the camera's capabilities. Between October 1st and 7th, CASIS captured multiple exposures, each 3 minutes long, tracking Atlas as it moved against the background stars. The comet appeared as a fuzzy white dot, slightly elongated, with a diffuse halo extending several thousand kilometers around the nucleus. The coma was clearly visible, proof that Atlas was actively outgassing even at this distance from the Sun. The images were not spectacular by Hubble standards, but they were valuable because they came from a completely different vantage point than any Earth-based observation could provide. Nick Thomas, the principal investigator for gases at the University of Bern, described the challenge. The comet was 10,000 to 100,000 times fainter than Mars, their usual target. Pointing a camera optimized for photographing a bright planet at a dim comet 30 million kilometers away was like using a microscope to examine the horizon. The exposure times were at the edge of what the instrument could handle. The signal was barely above the noise threshold, but they got it. A handful of pixels showing Atlas exactly where orbital predictions said it should be. Mars Express, ESA's older orbiter that had been studying Mars since 2003, also attempted observations. Its high-resolution stereo camera pointed toward Atlas during the flyby window. The camera was capable of detailed surface mapping from orbit, but the comet proved too faint. The images came back showing noise, star streaks, but no clear detection of Atlas itself. The spectrometers on Mars Express, Omega and SPECAM searched for spectral signatures. These instruments could potentially detect molecules in the coma even if the nucleus was too faint to image clearly. They observed during the predicted flyby times, capturing data that would take weeks to analyse fully. Initial results were ambiguous, marginal detections that might be real signals or might be instrumental artifacts. The signal-to-noise ratio was simply too low for definitive conclusions, but the geometry information was valuable. Knowing exactly where Mars Express was, exactly when it looked, and exactly what field of view it covered provided constraints. If Atlas had fragmented, if pieces had separated from the main nucleus, Mars Express should have seen multiple objects. The fact that it saw either nothing or only one faint target suggested the comet was still intact, not breaking apart as it approached the Sun. NASA's Mars Reconnaissance Orbiter was also positioned to observe. Its high-rise camera, the high-resolution imaging science experiment, has the sharpest vision of any camera ever sent to another planet. From Mars orbit, HiRISE can resolve features as small as a meter across on the Martian surface. Turned toward Atlas at 30 million kilometers, the spatial resolution was much coarser, roughly 30 kilometers per pixel. Given that Atlas's nucleus was estimated at 5 to 6 kilometers, the comet would appear as a sub-pixel target, a single overexposed point surrounded by the dimmer coma. But even a sub-pixel detection would be valuable, confirming the nucleus was still intact and measuring its exact position for trajectory refinement. As of the data we have, no high-rise images have been publicly released. That is not unusual. Mars orbiter data goes through a processing pipeline that takes time. Images get downlinked when bandwidth allows, pass through calibration software, undergo quality checks, and eventually end up in public archives. Weeks or months of latency is standard for non-urgent observations. The Perseverance rover sitting on the surface in Jezero crater also made an attempt. Its Mastcam-Z cameras can photograph the Martian sky, capturing images of clouds, dust devils, and celestial objects visible from the surface. On October the 1st, several Mastcam-Z images captured faint streaks in the sky roughly where Atlas should have been. Simeon Schmaus, an astrophotographer who follows Mars missions closely, downloaded those raw images from NASA's public archives. He stacked multiple frames and enhanced the contrast. The result showed a smudge at the predicted location. The timing matched, the position matched, but the signal was so faint that it could equally be a cosmic ray hit or image compression artifact. If genuine, it would be the only ground-level view of an interstellar object ever captured from another planet. A comet from beyond our solar system, photographed from the surface of Mars, while humans on Earth could not see it due to solar glare. The symbolism was striking even if the image quality was marginal. The attempt itself demonstrated how far Mars exploration has progressed. Rovers with cameras sophisticated enough to potentially photograph distant comets. Communication networks that allow raw images to reach Earth within hours. A global community of observers ready to process and enhance any data that might contain scientific value, even when that value was uncertain. The debate about that streak continued on social media and astronomy forums. Some argued it was definitely Atlas, pointing to the position and timing as evidence. Others were skeptical, noting that single-pixel anomalies in heavily processed images were not reliable evidence of anything. Without independent confirmation or better images, the question remained unresolved. China's Tianwen-1 orbiter and the UAE's Hope spacecraft were also near Mars during the flyby. Both missions carry cameras and spectrometers capable of observing celestial targets. Neither mission released data immediately. Tianwen-1 operates under different data-sharing protocols than Western space agencies. Results typically filter out through academic papers and press releases on timelines that do not match NASA or ESA schedules. HOPE, the United Arab Emirates Mars mission, focuses primarily on atmospheric science. Its instruments are optimized for studying how gases circulate in Mars's thin atmosphere. Observing a distant comet was possible, but not part of the primary mission objectives. If HOPE captured useful data, it would likely appear in scientific publications months or years later, after the team had time to analyze it properly. The real value from the Mars flyby was not in spectacular images or groundbreaking spectroscopy. It was in confirmation. Atlas was where it was supposed to be, doing what comets do. The coma was active and visible. The orbit matched predictions within measurement uncertainties. No fragmentation, no secondary objects, no evidence of anything beyond a single comet on a hyperbolic trajectory, except for one detail that researchers noticed but hesitated to emphasize publicly. The coma was larger than models predicted. Based on the solar flux at 2.9 astronomical units and the estimated nucleus size, the coma should have been about 2,000 to 3,000 kilometers in diameter. The CASIS images suggested 4,000 to 5,000 kilometers. That discrepancy was not huge. Coma size estimates are inherently uncertain. They depend on exposure time, detector sensitivity, and how you define the boundary between coma and background. You're measuring something diffuse and fuzzy with no sharp edge. Different astronomers looking at the same image might draw the boundary in slightly different places. But 4,000 to 5,000 kilometers was noticeably larger than expected. If you trusted the models and the nucleus size estimate, something was producing more gas and dust than the heating alone could explain. One explanation was that the nucleus was more active than assumed. The 8% surface coverage releasing volatiles might be conservative. Perhaps 10 or 12% of the surface was outgassing, driving a larger coma. That would still be unusual, but not impossible. Another explanation was the ice debris field. Those chunks floating in the coma, each one sublimating independently, could expand the effective outgassing region beyond the nucleus itself. The total gas production would include contributions from the nucleus and from hundreds or thousands of small ice fragments scattered through the coma. A third explanation, the one that appeared in private conversations but not in public statements, was that Atlas had done something at Mars. Released material, vented gas, performed a maneuver that temporarily increased coma production. There was no evidence for this, none whatsoever. But the oversized coma was ambiguous enough to support multiple interpretations without confirming any of them. The Nomad spectrometer on the trace gas orbiter represented another opportunity. Nomad was designed to measure trace gases in Mars's atmosphere with high sensitivity. It could potentially detect molecules in Atlas's coma if viewing geometry allowed. The observations were challenging. Nomad typically looks at Mars's atmosphere using sunlight passing through to reveal spectral absorption lines. Pointing at a comet required different configurations the instrument was not designed for. The data was collected but remained in processing. Extracting signal from observations that pushed the instrument to its limits required careful calibration. The team worked methodically, but results would not be available for months. If Nomad succeeded in capturing spectral lines during the flyby, the data would complement earlier observations from JWST and other telescopes. Different viewing geometry and illumination conditions would help build a three-dimensional picture of molecular distribution through the coma. The Mars flyby also tested coordination protocols. Atlas was moving at 67 km per second relative to the Sun. Pointing spacecraft at a fast-moving target required precise ephemerids, real-time updates, and perfect timing. The Mars orbiters succeeded. CASIS captured Atlas exactly where predictions placed it. That success validated observation planning and demonstrated multi-agency coordination on a target, allowing no second chances. This would feed into November observations. When JWST observed Atlas after perihelion, coordination would be even more critical. The comet would be brighter but also more variable, potentially fragmented. The Mars flyby was the dress rehearsal. The main event was ahead. As October progressed, Atlas moved deeper inward. The geometry shifted. The comet pulled away from Mars, heading sunward. The orbiters returned to normal routines. The brief distraction passed. Mars returned to being Mars, alone in its orbit. But the data remained, stored in archives, images showing that oversized coma, spectra that might contain molecular signatures, geometric constraints proving Atlas was intact on October 3rd, and the question lingered. If the coma was larger than expected, if the comet was producing more gas than solar heating could explain, what did that mean? Natural variability? Or evidence of something else, some process not accounted for in standard physics? The Mars flyby could not answer that question. It could only document what was happening and preserve the data for future researchers to puzzle over. Chapter 6. Into the Fire. Solar conjunction is not supposed to be dramatic. Most comets pass behind the Sun, disappear from view for a few days or weeks, then emerge on the other side looking predictably different. Brighter if they survived, fragmented if they did not. Astronomers have watched this pattern for centuries. The physics is well understood, the outcomes are usually anticipated. But Atlas was reaching perihelion at 1.36 astronomical units on October 29th, completely hidden behind solar glare. And the uncertainty about what would happen was driving the astronomical community into territory where confidence gave way to speculation. The geometry was cruel. Earth and the comet sat on opposite sides of the Sun with an angular separation that made ground-based observation impossible. You cannot point a telescope at an object 12 degrees from the Sun without destroying the instrument or blinding the detectors. Solar glare overwhelms everything. Even space-based telescopes like Hubble have strict solar exclusion zones. SOHO and other coronagraphs might catch a glimpse, but Atlas was expected to be too faint, too far from the solar limb to register against scattered light. For approximately 6 weeks, from early October through mid-November, humanity would be blind to what was happening. The comet would undergo its most dramatic transformation out of sight, beyond reach, unknowable, until it emerged. But perihelion is not just about visibility, it is about physics. At 1.36 astronomical units, the solar flux becomes intense enough to vaporize every volatile compound on the comet's surface. Water ice sublimates aggressively. Carbon dioxide, which had dominated the coma based on JWST observations, transitions from solid to vapor almost instantaneously. Carbon monoxide, ammonia, methane, any supervolatiles trapped in the ice matrix, all release simultaneously. The nucleus becomes a pressure cooker. Gas escapes through cracks and vents. Dust lifts on expanding vapor. The coma swells to millions of kilometers. The tail stretches behind like a banner, pushed by solar radiation pressure and the solar wind. This is the model, the prediction every textbook makes about what happens at perihelion. But the model assumes we understand the composition and structure of Atlas, and we do not. Not really. The JWST data from August revealed that 8:1 carbon dioxide to water ratio. That extreme composition changes everything about how perihelion should behave. Carbon dioxide ice sublimes at much lower temperatures than water ice. At 1.36 astronomical units, the surface temperature on the sunward side could reach 200 Kelvin or higher. That is well above the sublimation point for carbon dioxide, which kicks in around 150 Kelvin. Water ice needs closer to 270 Kelvin to sublimate efficiently, so there is a decoupling. The carbon dioxide explodes off the surface immediately, creating a massive outburst. The water, buried underneath or mixed into the ice matrix, sublimates more slowly. The result is a two-stage event. First, a violent burst of carbon dioxide creating a bright, rapidly expanding coma. Then, a slower, sustained release of water vapor as surface layers erode and expose deeper ice. But here is where it gets complicated. If the carbon dioxide dominates and erupts violently, it could blow away the surface dust layers that insulate underlying water ice. Once that insulation is gone, solar radiation penetrates deeper. Water sublimation accelerates. The comet could transition from carbon dioxide dominated to water dominated in hours or days, and we would not see it happen. We would only see the aftermath when observations resumed in November. There is another scenario, one discussed quietly but rarely in formal papers. What if the comet fragments? Perihelion stress is real. The combination of thermal shock, internal pressure from outgassing, and tidal forces from solar gravity can tear weakly bound objects apart. The history is littered with examples. Shoemaker-Levy 9 shattered into more than 20 pieces before impacting Jupiter in 1994. Comet Biela split in the 1840s and never reformed. More recently, Comet Atlas C2019Y4 disintegrated in 2020 as it approached the Sun, falling apart into a cloud of debris that dispersed and faded. Atlas has a rotation period of 16.16 hours. That is slow enough that centrifugal forces are negligible. Gravity should hold it together easily. But the object has been travelling through interstellar space for billions of years. Cosmic ray bombardment, temperature cycling between near absolute zero and whatever warmth it absorbed near other stars, micrometeorite impacts, internal voids from volatile loss over geological timescales. The structural integrity could be compromised in ways we cannot detect from spectroscopy or photometry. If it fragments, the light curve will reveal it immediately. A sudden brightening as more surface area gets exposed, then a rapid fade as fragments disperse and total cross-section decreases. By the time JWST observes in November, we would see multiple condensations, separate nuclei each with their own coma, strung out along the orbital path like pearls on a string. That would be spectacular from a scientific perspective. Multiple samples from the interior of an interstellar comet, different layers exposed, compositional gradients laid bare. But it would also mean we missed the fragmentation event itself. The moment of breakup, the forces involved, the way material separated, all of that happened behind the Sun where we could not document it. Then there is Loeb's scenario, the one that treats perihelion as opportunity rather than hazard. If Atlas is technological, if it has any capability for propulsion or maneuvering, perihelion is when you use it. The Oberth effect amplifies every kilogram of thrust. A small burn at perihelion produces velocity changes that would require orders of magnitude more fuel at aphelion. If the goal is releasing probes that capture interplanetary orbits, you release them here. The mathematics is unambiguous. October 29th is the optimal window. Loeb calculated the exact parameters. A 10-kilogram probe with a chemical rocket providing 500 meters per second of delta V could insert into a highly elliptical Earth orbit with periapsis around 400 kilometers and apoapsis beyond the Moon. From that orbit, the probe could study Earth's atmosphere, oceans, electromagnetic emissions, anything visible from space. It could transmit data back to Atlas before the mothership exits the solar system, or remain dormant, waiting, observing, recording for later retrieval. The arrival window would be late November, between the 21st and December 5th, depending on exact release point and trajectory. That assumed minimal correction burns during transit. If the probes have more fuel, more sophisticated guidance, the window expands. We could see them earlier or later, we could miss them entirely if they maneuver to avoid detection. And here is the uncomfortable question. Would we even recognize them? Our space surveillance network tracks catalogued objects, satellites, debris, spent rocket stages. We know where they are and where they should be based on orbital mechanics. Something new appearing in an unexpected orbit would trigger alerts. But the response time is not instantaneous. By the time we identified an anomaly, investigated its origin, ruled out natural explanations, the probe could have completed its mission and changed orbits again. The Galileo Project observatories would monitor for exactly this. 3 sites running continuous all-sky surveys in optical, infrared and radio wavelengths. Any transient event, any object moving in ways that defy standard ballistic trajectories gets flagged for analysis. During November and December, detection thresholds would be lowered. False positives would increase, but so would sensitivity. If something arrives, they would see it. NASA and ESA have not officially commented on this aspect. Their focus remains on the natural comet hypothesis. But behind closed doors, people pay attention. Space agencies have protocols for unidentified objects. Not UFO protocols, not alien contact scenarios, but engineering protocols for unexpected debris, untracked satellites, potential collisions. Those protocols can adapt. If an object appears in Earth orbit with no launch history, no catalogue entry, no plausible natural origin, protocols activate. Tracking intensifies. Military assets get involved. The international community starts asking questions. As October progressed in 2025, the moment everyone had anticipated arrived. October 29th approaches. Atlas is already invisible, swallowed by solar glare. The last ground-based observations were in late September. Mars orbiters caught it during the October 3rd flyby, but those images showed a comet behaving normally. Visible coma, dust production consistent with solar heating, nothing anomalous. nothing screaming technology or fragmentation or crisis. But perihelion is different. Perihelion is where thermal stress peaks, where internal pressures exceed structural limits, where decisions get made if decisions are possible. In 6 days, Atlas will be closer to the Sun than it has been in its entire multi-billion-year existence. Surface temperature will spike, outgassing rate will explode, and we will not see any of it. The only real-time data will come from heliospheric observatories. Parker Solar Probe is nowhere near the right position, but Stereo and SOHO might catch something. Scattered light observations, brightness fluctuations. If Atlas produces a major outburst, if the Comet expands rapidly enough, the solar monitoring satellites could detect changes in scattered solar radiation. It would be indirect, low resolution, but it would be something. A data point during the blind period. Then we wait for JWST. The spacecraft is positioned perfectly for post-perihelion observations. Between November 2nd and 25th, it will observe with multiple instruments. Janus cameras for imaging, MAGIS spectrometer for compositional analysis, PEP particle detector for coma environment, UVS ultraviolet spectrograph for volatile identification. All of it pointed at Atlas as it emerges from behind the Sun, still bright from perihelion heating, potentially fragmented, potentially trailing a spectacular tail, potentially doing something no one predicted, but the data will not arrive until February 2026. JWST is using its high-gain antenna as a heat shield right now, relying on medium-gain antenna for communication. Data rate is slow. Observations take priority over transmission. The images and spectra get stored on board, queued for download when bandwidth allows. By the time we see what JWST saw in November, Atlas will be past Venus, heading back toward the asteroid belt, already cooling and fading. 3 months of latency. 3 months of speculation and competing interpretations. Did it survive? Did it fragment? Did anything unusual happen behind the Sun? The answer exists right now in photons travelling from JWST to Earth at light speed. But we cannot access it. We cannot know until data arrives, gets processed, and releases to the community. That is the cost of observation at interstellar distances with solar system spacecraft. We get unprecedented views from unique vantage points, but we pay for it in time, in waiting, in uncertainty stretched across months instead of hours. October 29th is the inflection point. Before that date, Atlas is a comet approaching the Sun. Unusual but explicable, interesting but not revolutionary. After that date, it becomes whatever perihelion made it. A fragmented debris field, a brightened comet with massive tail, a dormant object that survived intact but inactive, or something else, something requiring new categories and new terminology, and new frameworks for interpretation. The Sun hides the answer, not forever, just long enough to make the waiting unbearable. What we know is limited to physics and probability. The solar flux at 1.36 astronomical units delivers roughly 540 watts per square metre to the sunward surface. For a nucleus 5 kilometres across, assuming half the surface faces the Sun, that is about 10 billion watts of total power input. Most of that energy goes into heating the surface. Some fraction drives sublimation. The efficiency depends on the composition, the porosity, the thermal conductivity of the material. For typical cometary ice, maybe 10 to 20% of incoming energy goes into vaporization. The rest heats the material and radiates back into space. 10% of 10 billion watts is 1 billion watts going into sublimation. Water ice has a latent heat of sublimation around 2.8 million joules per kilogram. Carbon dioxide is about 590,000 joules per kilogram. If the ice is mostly carbon dioxide, 1 billion watts translates to roughly 1,700 kilograms per second of mass loss at perihelion. That is 40 times higher than what Swift measured at 2.9 astronomical units. The outgassing rate should explode. 1,700 kilograms per second is a fire hose, a geyser. The coma should balloon to millions of kilometers. The tail should extend for tens of millions of kilometers, bright enough to see from Earth if it were not hidden by solar glare, unless the volatiles exhaust, unless active regions shut down, unless something unexpected happens. Comets are not simple. They have layers, internal structure, variations in composition. The surface might be depleted in volatiles while the interior remains ice-rich. Cracks and vents channel gas from deep inside, creating jets that do not correlate with local surface temperature. Atlas could behave in ways that defy prediction because we have never studied an object like this before. A thick-disk comet with extreme carbon dioxide dominance that spent 10 billion years in interstellar space. Our models are built on solar system comets. Applying those models to Atlas is extrapolation. It probably works, but probably leaves room for surprises. The hidden perihelion passage represents a gap in human knowledge that cannot be filled retroactively. Whatever happens on October 29th stays unknown until JWST data arrives months later. We can model and predict, but we cannot observe, and observation is the foundation of science. Without it, we wait for confirmation that may or may not align with expectations. Atlas moves toward that moment, accelerating as solar gravity pulls it inward, heating as radiation intensity increases. The nucleus experiences warmth it has not felt since leaving its parent star system. The ice responds, molecules break free, gas pressure builds, cracks propagate, and somewhere in the dark, hidden from view, the transformation begins. Chapter 7. The Scientist vs. the Maverick. 2 Harvard PhDs, same data, completely opposite conclusions. One says it is definitely a comet. The other calculated a 40% chance we just witnessed first contact. Who is right? The answer reveals everything about how science really works. Tom Statler did not mince words. NASA's lead scientist for solar system small bodies was asked directly about the technological artifact hypothesis during a media briefing. His response was blunt. It looks like a comet. It does comet things. It very, very strongly resembles in just about every way the comets that we know. The emphasis on very, very was deliberate. This was not diplomatic hedging. This was a scientist drawing a line and saying enough. The frustration in the astronomy community is palpable, not because Loeb is asking questions. Questions are fine. Questions are what science runs on. The frustration comes from how those questions get amplified, how a hypothesis with low probability gets treated by media and social platforms as if it has equal weight to the mountain of evidence pointing toward natural origin. How every new observation, every spectrum, every image has to be filtered through the alien probe narrative before the actual science can be discussed. Chris Lintott at Oxford was even less diplomatic. He called the technological hypothesis absolute nonsense on stilts, an insult to the exciting work going on to understand this object. Lintott was part of the team that traced Atlas back to the thick disk. He spent months analysing trajectory data, running population simulations, publishing results that advance understanding of galactic dynamics and interstellar object origins. And then he watches those results get buried under headlines about alien motherships and mini-probes. The scientific community's investment in rigorous analysis gets overshadowed by speculation that requires no evidence and makes no testable predictions. Jason Wright at Penn State took a different approach. He wrote a detailed blog post systematically addressing each of Loeb's claimed anomalies, point by point, data set by data set. Wright is not hostile to technosignature research. He works on it himself. He is part of the community searching for evidence of extraterrestrial intelligence, but he is also a careful scientist who insists on standards, and by those standards, Atlas fails every test. Start with the brightness issue. The claim that early photometry suggested a 20-kilometer object, therefore it must be something else. Wright points out this is cherry-picking. Early observations were low resolution, taken when the comet was faint and distant. As better instruments got longer exposures, size estimates converged on 5 to 6 kilometers. That is normal observational refinement, not a mystery requiring exotic explanations. The claim about missing cometary signatures in early spectra. Wright dug into those papers. The observations were marginal, signal to noise barely above detection threshold. The absence of clear molecular lines was not proof of unusual composition. It was proof that the comet was too faint for definitive spectroscopy at that distance. Once JWST and other major instruments locked on, the signatures appeared. Water, carbon dioxide, carbon monoxide, carbonyl sulfide, all exactly what you expect from a comet. The initial ambiguity was observational limitation, not physical reality. The trajectory probability of 0.005%. Wright ran the numbers independently. The calculation depends heavily on how you define close approach. If you use realistic detection thresholds, Accounting for the fact that we can only see objects above certain brightness limits, the probability increases substantially. You're not calculating the odds of any random object passing near 3 planets. You're calculating the odds that an object bright enough to detect passes near 3 planets. That is a much less restrictive condition. The probability is still low, but not absurdly low, not 5 sigma anomalous. Then there is the dust configuration issue. The claim that sunward dust emission requires active propulsion or venting. Wright points to decades of cometary science showing that dust distributions are complex. Jet activity is never uniform. Rotation axis orientation matters. Local variations in volatile content create asymmetric outgassing. The specific pattern seen in Atlas might be unusual, but it is within the range of natural behaviour. Dozens of solar system comets show similar features. Nobody invokes alien technology to explain them. The rotation period argument falls apart under scrutiny. 16.16 hours is unremarkable for a comet this size. It is stable against breakup. It is consistent with either a rubble pile or a solid object. It tells us nothing about artificial versus natural origin because both would have similar rotation dynamics. Using it as evidence for technology is like saying a rock is artificial because it is round. Roundness can be natural or shaped. Rotation period can be natural or designed. The measurement itself is agnostic. Wright reserves his sharpest criticism for the approach angle argument. The claim that coming from Sagittarius, from the direction of the galactic centre, is tactically smart for avoiding early detection. This is retrofitting intent onto geometry. Atlas approached from that direction because that is the direction it was travelling. If it had come from Ursa Major, we would hear arguments about how that region is strategically optimal for some other reason. The logic is unfalsifiable. Any approach direction can be spun as intentional. That is not science. That is storytelling. But the most damaging critique comes from the absence of what should be there if the hypothesis were true. If Atlas is a technological artifact, it should emit waste heat. Any active system, any electronics, any propulsion generates heat. That heat has to radiate away. At wavelengths corresponding to a few hundred Kelvin, infrared telescopes should detect thermal emission that does not match solar heating alone. Multiple infrared observations have been done, Spitzer before it was retired, JWST, Sphere-X, ground-based infrared telescopes. All of them show thermal emission consistent with a cold, icy body warmed by the sun. No excess, no anomaly. Just a comet doing what comets do. If there is propulsion, we should see it. Spectroscopically, chemically. Trajectory changes that exceed what outgassing can produce. Atlas has been tracked continuously since discovery. The orbit is known to high precision. Any deviation from a purely gravitational trajectory would be obvious. There is none. The comet is following Newtonian mechanics perfectly. No burns, no course corrections, no evidence of active control. If there is communication, we should detect it. Radio emissions, laser pulses, modulated light. The SETI community has been listening. Multiple radio telescopes have pointed at Atlas during its approach. Greenbank Telescope, Allen Telescope Array, Parkes in Australia. All of them searching across wide frequency bands for any hint of artificial signal. The result is silence, complete, total. Not even ambiguous noise that could be interpreted generously. Just the background hiss of the universe with no artificial component. Every test that could distinguish technology from natural origin has been performed. Every test came back negative. At some point, the burden of proof shifts. It is no longer enough to point at low probability coincidences and demand that natural explanations account for them. You need positive evidence, a detection, a measurement, something that cannot be explained by a comet and requires invoking technology. That evidence does not exist. Statler made this point explicitly. We have extraordinary instruments. We have been observing Atlas intensely for months. If there were anything genuinely anomalous, anything that broke the comet model in a way that required new physics or new classifications, we would have found it. The fact that we have not is itself evidence. Not proof, but evidence weighted heavily toward natural origin. The scientific community's response has been measured but firm. Papers get published, data gets shared, observations continue. But there is an unspoken agreement that the technological hypothesis does not warrant serious engagement anymore. It has been tested, it failed. Continuing to debate it is a distraction from the actual scientific opportunities Atlas presents. Because those opportunities are immense, this is the first thick-disk comet ever studied, the first object with an 8:1 carbon dioxide to water ratio, the first interstellar visitor observed by JWST and SphereX and Mars orbiters simultaneously. The compositional data alone could refine models of planet formation in ancient star systems. The trajectory data improves our understanding of galactic dynamics and ejection mechanisms. The outgassing behavior challenges assumptions about cometary activity and volatile distribution. But all of that gets buried when the conversation keeps circling back to alien probes. Scientists are tired of it. Tired of spending time debunking claims that should never have gained traction. Tired of watching their work get ignored because it is not sensational enough. Tired of the implication that they are closed-minded for insisting on evidence before accepting extraordinary claims. Lintot's comment about insult is telling. The teams working on Atlas are some of the best observational astronomers in the world. They are using cutting-edge instruments, publishing in top journals, doing exactly what science is supposed to do. Observe, analyze, draw conclusions based on data. And then they get told they are missing the obvious, that they are so wedded to conventional thinking they cannot see what is right in front of them. It is infuriating. There is also a deeper concern. The public takeaway from this entire episode is that scientists dismissed the alien hypothesis without properly investigating. That is backwards. The investigation was exhaustive. Multiple teams, multiple instruments, months of effort. The hypothesis was taken seriously, tested rigorously, and found wanting. But because the tests were technical, because the null results did not generate headlines, the public perception is that scientists are being dismissive rather than thorough. That perception damages science. It reinforces the idea that mainstream astronomy is too conservative, too afraid of paradigm shifts, too invested in protecting existing theories. And that is not true. Astronomers would love to find evidence of extraterrestrial technology. It would be the discovery of the millennium, Nobel Prizes, textbooks rewritten, a complete transformation of how we understand our place in the universe. The motivation is there. The will is there. What is missing is evidence, Wright summed it up in his blog post. The burden of extraordinary proof lies with extraordinary claims, not the other way around. Science does not work by demanding natural explanations provide absolute certainty before considering alternatives. It works by accumulating evidence and following it wherever it leads. And right now, all the evidence leads to a comet, an unusual comet, an interesting comet, a scientifically valuable comet, but a comet. Loeb, for his part, has not backed down. He acknowledges that the probability of Atlas being artificial is low. He never claimed certainty. What he claims is that the probability is non-zero, and that non-zero probabilities deserve investigation. He points to the history of science, to discoveries that were initially dismissed because they contradicted prevailing theories. Continental drift, quasi-crystals, high-temperature superconductors, all of them face skepticism, and all turned out to be real. But for every revolutionary idea that was initially dismissed and later vindicated, there are thousands that were dismissed and stayed dismissed because they were wrong. Cherry-picking success stories does not prove that current skepticism is misguided. The difference between revolutionary science and fringe speculation is evidence. When Wegener proposed continental drift, he had evidence. Matching coastlines, similar fossils on different continents, geological formations that lined up across oceans. The evidence was initially insufficient to convince the community, but it existed and accumulated over time until acceptance became inevitable. Loeb has calculations showing that certain scenarios are possible, that probes could be released at perihelion, that arrival windows would fall in November and December, that coordination protocols exist for tracking unidentified objects. But possibility is not evidence. Showing that something could happen is not the same as showing it did happen. The Galileo Project observatories will watch the sky during the predicted arrival window. If something appears, if an object shows up that cannot be explained naturally, the conversation changes immediately. Scientists adapt. New hypotheses get proposed. Testable predictions get made. That is how science progresses. Through evidence, not speculation. Until then, the technological hypothesis remains what it has always been. A possibility with vanishingly low probability, unsupported by data, sustained by motivated reasoning rather than empirical foundation. and the scientists studying Atlas will continue their work, documenting this remarkable visitor from the thick disk, extracting every bit of information before it disappears into interstellar space, with or without the alien narrative, with or without the headlines, because that is what scientists do. The debate has revealed something about science communication. The internet democratized access to information, but made it harder to distinguish expert consensus from fringe speculation. Social media algorithms favor engagement over accuracy. Controversy generates clicks. Sensational claims spread faster than careful rebuttals. In that environment, a hypothesis like Loeb's finds fertile ground. It is interesting. It is provocative. It taps into deep human desires to not be alone. And it comes from a credentialed scientist at a prestigious institution, lending legitimacy. But credentials do not make claims true. Harvard professors can be wrong. Nobel laureates can be wrong. What matters is evidence, methods, reproducibility. And on those grounds, the case for Atlas being artificial collapses. The trajectory probability, while low, is not impossibly low given detection biases and small sample size. The chemistry, while unusual, fits natural formation scenarios for comets from ancient systems. The brightness variations, rotation period, dust distribution all have precedent in solar system comets. The absence of excess heat, lack of trajectory deviations, silence in radio observations all argue against active technology. Every anomaly Loeb identifies has alternative natural explanations, making technology unnecessary. Occam's razor applies. When you have two explanations and one requires only known physics, while the other requires unknown technology, choose the simpler until evidence forces otherwise. Chapter 8. When the Internet Panics, September 29, 2025. A TikTok video, dramatic music, stock footage, text overlay, Atlas on collision course with Earth, NASA hiding the truth, impact expected. October 22nd. 2 million views in 48 hours. The post was completely false, but that did not matter. The collision claim was easy to debunk. Atlas's closest approach to Earth is 1.8 astronomical units. That is 270 million kilometers, more than half again the Earth-Sun distance. It never comes anywhere near us. The orbital mechanics are public. NASA publishes ephemerides. Anyone with basic software can verify the trajectory, but facts do not spread as fast as fear. Fast. The debunking videos got a few 100,000 views. The panic video kept circulating. It continued to circulate for months afterward, still generating comments from people who thought October 22nd was doomsday. Then came the remote viewing claims. An account called NY Crypto King posted on X that they had remote viewed Atlas. Claimed to see structures inside, microbial life being carried in ice pockets, a signal broadcasting at frequencies we have not detected yet. The post included detailed descriptions of the interior composition, the arrangement of technological components disguised as natural materials, and a warning that probes would deploy on October 29th, dropping microbes into Earth's atmosphere as part of a terraforming operation. Remote viewing is pseudoscience. Controlled experiments have repeatedly shown it does not work. Nobody can see distant objects through psychic means, but the post got traction anyway. 30,000 likes, 15,000 retweets. People treating it as credible intelligence, building theories around it, cross-referencing it with other conspiracy frameworks. The signal claim was particularly viral. Multiple amateur radio enthusiasts started monitoring frequencies they thought might carry the broadcast. They found nothing but convinced themselves the signal was encrypted or using modulation schemes beyond human technology. 4chan entered the conversation with a post claiming insider knowledge. An anonymous user identifying as a European astronomer said Atlas was not a comet or a spaceship. It was a bubble of dark matter or dark energy left over from the Big Bang. The object did not reflect sunlight. It absorbed energy from the quantum vacuum. It was heading toward Earth to merge with the planet's core and trigger a dimensional shift. The post was obviously fiction. The physics made no sense. Dark matter does not form bubbles. It does not absorb vacuum energy. But the post got screenshotted and shared across platforms as if it were leaked classified information. The Jeffrey Epstein connection appeared in early October. Someone on Reddit noticed that Loeb's first major paper on Atlas was published 72 years after Epstein's birth. They calculated that the comet's discovery date, July 1st, was significant in numerology. added some cherry-picked correlations between orbital parameters and dates relevant to Epstein's life, concluded that the entire Atlas event was manufactured to distract from renewed interest in Epstein files. The conspiracy theory made no sense. Comets do not get discovered on predetermined dates to serve political agendas, but it spread anyway, blended into QAnon frameworks, got cited as evidence of deep state manipulation. Other variants targeted Loeb directly. Posts claiming his analysis was discredited because of his Jewish heritage, because of Israeli connections, because Harvard receives funding from sources tied to whatever geopolitical enemy the poster wanted to invoke. These were not good faith criticisms. They were anti-Semitic attacks dressed up as skepticism. Loeb addressed them in a blog post, pointed out that Atlas exists independent of his identity, that the object can be observed by anyone with a telescope, that his ethnicity and nationality have zero bearing on the physics. But engaging with bigotry is exhausting. The posts kept coming. The NASA shutdown angle became a major talking point. In early October, the US government shutdown began. NASA's Public Affairs Office stopped updating websites and social media. Press releases slowed. The temporary communication blackout coincided with Atlas approaching Mars and slipping behind the Sun. Conspiracy theorists saw causation. The shutdown was deliberate. Time to prevent NASA from having to answer questions about what the Mars orbiters saw during the flyby. The agency was suppressing data, hiding images that showed fragmentation or probe deployment, or something else they did not want public. In reality, government shutdowns are political failures, not calculated cover-ups. They happen when budget negotiations collapse. The timing was coincidental. NASA was not hiding anything. The Mars orbiter data takes weeks to process under normal circumstances. The shutdown delayed things further, but not because of censorship, because staff were furloughed and the pipeline stopped moving. When the government reopened, the images were released. They showed a comet exactly as expected. But by then, the narrative was set. The delay was proof of conspiracy regardless of what the data eventually showed. Al Jazeera's Sanad fact-checking unit investigated claims circulating in Arabic-language social media. Posts saying Atlas would impact Earth on October 22nd, that its tail would poison the atmosphere, that electromagnetic pulses from the comet would disable all electronics globally. That religious prophecy predicted this event and the signs were aligning. Sanad traced the claims back to mistranslations and deliberate fabrications, published detailed debunking with source citations and expert quotes. The fact-check reached maybe 10% of the audience the original false claims reached. A viral post on Facebook claimed Atlas triggered a military emergency meeting. World leaders convened in secret. Defense systems were being activated. Quotes attributed to unnamed Pentagon officials suggesting the comet posed a national security threat. The post linked to a YouTube video, 3 million views, 40-minute runtime, a narrator explaining how Atlas was detected by classified military satellites before civilian astronomers saw it, how the trajectory was initially suppressed, how insiders leaked information through back channels, none of it true, all of it presented with ominous music and authoritative tone that made it feel credible. The religious angle became prominent, Christian posts interpreting Atlas as a sign of end times, Revelation references, Wormwood connections, the comet as harbinger of judgment, Islamic posts discussing similar themes through different scriptural lenses, Hindu interpretations involving cosmic cycles and avatars. People across belief systems projecting apocalyptic narratives onto an object that is just ice and rock. The need to find meaning in celestial events is ancient. Comets have always been omens. Atlas is no different. Except now the omens spread globally in hours instead of taking years to filter through societies. Meme culture contributed. Images of Atlas labelled as various things. The homework I forgot to turn in finally showing up. My problems arriving right on schedule. Alien tourists coming to check if Earth is worth visiting and deciding to leave. The memes were harmless, often funny, but they reinforced the idea that Atlas was a character in a story rather than a scientific object. That it had agency, intent, personality. The anthropomorphization made it harder to engage with the actual data. People were relating to the comet emotionally rather than analytically. The polarization was stark. On one side, astronomers and science communicators trying to share accurate information, spectra, orbital calculations, composition analysis. On the other side, a tsunami of speculation, conspiracy, fear, and wishful thinking. the two groups barely overlapped. They occupied different information ecosystems, different platforms, different epistemic standards. A person could spend hours consuming content about Atlas and never encounter a single accurate fact. Twitter community notes tried to keep up, adding context to viral posts, linking to NASA pages, providing orbital data to counter collision claims. But community notes only appear after a post has already gone viral. The correction reaches a fraction of the audience, and motivated reasoning is powerful. People who want to believe in the alien mothership hypothesis find ways to dismiss corrections. NASA is lying. Scientists are closed-minded. The official story does not add up. Anything that contradicts the preferred narrative gets filtered out. YouTube became a battleground. Science channels trying to explain what Atlas actually is, what the observations show, what the chemistry means. Those videos struggled to break 100,000 views. Meanwhile, conspiracy channels with dramatic thumbnails and sensational titles pulled millions. The algorithm favors engagement over accuracy. Fear drives engagement more effectively than education, so the misinformation gets promoted, amplified, monetized. Reddit communities split along predictable lines. The astronomy and space subreddits maintained sanity. Moderators removing conspiracy posts, users debunking claims with citations, civil discussion about trajectory uncertainties and spectroscopic methods. But other subreddits, the ones focused on UFOs and conspiracy and fringe topics, became echo chambers. Any skepticism got downvoted. Any link to mainstream science got dismissed as propaganda. The communities self-radicalized, convinced each other that they understood the truth while everyone else was blind or complicit. Instagram influencers with no scientific background posted confident explanations of Atlas. Many got basic facts wrong, confused astronomical units with light years, claimed the comet was visible to naked eye when it never was, mixed up Atlas with other objects, but they had audiences, hundreds of thousands of followers who trusted them, who shared their posts, who treated influencer speculation as equivalent to peer-reviewed research. The misinformation had real consequences. Astronomy educators fielding panicked emails from concerned parents and students. Teachers trying to calm classrooms full of students who genuinely thought the world was ending. Mental health professionals dealing with anxiety triggered by apocalyptic narratives. The damage was not hypothetical. It was measurable, quantifiable in the time wasted correcting falsehoods and the psychological distress inflicted on vulnerable people. Some of the conspiracy thinking was performance trolling. People who knew better but enjoyed creating chaos. But some of it was genuine. True believers convinced that Atlas represented first contact or existential threat or divine intervention. Those people doubled down when contradicted, sought out information that confirmed their views, built elaborate frameworks connecting Atlas to other conspiracies. The object became a symbol, a blank screen onto which people projected whatever fears or hopes or fantasies they carried. By mid-October, Atlas had transcended its identity as a comet. It was a cultural phenomenon, a mirror reflecting how society processes information in the age of social media, how truth and fiction blend, how expertise gets devalued, how fear spreads faster than understanding. The actual object, the 5-kilometer ball of ancient ice and rock currently hidden behind the sun, became almost irrelevant to the narrative swirling around it. And the scientists studying Atlas could only watch. They could publish papers, give interviews, post corrections, but they could not control the story. The story had escaped, mutated, become something beyond their reach. All they could do was continue the work, document the observations, analyze the data. Trust that eventually, long after the social media frenzy faded, the scientific record would remain accurate, preserved, a counterweight to the chaos. The episode revealed something troubling about modern information ecosystems. Not just that misinformation spreads, but that corrections struggle to gain traction even when they are accurate and well-sourced. The architecture of social media favors the first version of a story over subsequent corrections. Once a narrative establishes itself, once it gets embedded in enough minds and referenced in enough posts, dislodging it becomes nearly impossible. People build their understanding on top of false foundations. When you point out the foundation is wrong, they defend it because abandoning it would mean rebuilding everything they thought they knew. The Atlas case highlighted the gap between what scientists know and what the public perceives. To astronomers, the observations were exciting but explicable. An unusual comet with interesting chemistry, valuable science, but nothing revolutionary. To large segments of the public, it was first contact or doomsday or conspiracy. The gap is enormous. When people do not trust institutions, when they feel disconnected from experts, when their information diet consists of social media rather than primary sources, misinformation fills the vacuum. Not because people are stupid, but because humans crave coherent narratives even when data is incomplete. Atlas became a canvas for those narratives. It arrived when distrust of authority was high, when conspiracy thinking had gone mainstream. In that context, a Harvard professor suggesting the comet might be artificial was not just scientific speculation. It was validation for people who already believed institutions were hiding truth. The scientists who pushed back found themselves cast as closed-minded gatekeepers, not because their science was wrong, but because their message was less emotionally satisfying than alternatives. People want wonder, they want significance. A comet that is just a comet, however ancient, does not provide that emotional payoff. A comet that might be a spaceship does. And so the narrative persisted, fueled by hope and fear and the human need for meaning. Impervious to correction because correction felt like taking something away rather than adding clarity. By the time Atlas emerged from behind the sun in November, the online conversation had moved to other topics. The comet would remain in the news briefly, but peak attention had passed. The scientists would continue analyzing data, publishing papers, refining models. The misinformation would persist in archived posts, available to future conspiracy theorists. And the next interstellar object would trigger the same cycle. The same speculation, the same conspiracies, the same battle between evidence and imagination. Because that is how it works now. Where algorithms reward engagement over truth, every unusual event becomes a canvas for collective projection. Atlas did not change that. It only revealed it, clearly and undeniably. Chapter 9. Waiting for Revelation, November 4th, 2025. 428,000 kilometers from Atlas, the JWST spacecraft began its observations. The Jupiter Icy Moons Explorer, designed to study Europa, Ganymede, and Callisto years from now, had pivoted its instruments toward an unexpected target, an interstellar visitor emerging from its closest encounter with the Sun. This was the moment the astronomical community had been waiting for. The hidden perihelion passage was over. Atlas had survived, emerged from behind the solar glare, and now one of humanity's most sophisticated spacecraft had a clear view. The instrument suite was formidable. Janus, the optical camera system, would image the nucleus and coma at resolutions no Earth-based telescope could match during this period. Magis, the imaging spectrometer, would map composition across infrared wavelengths, tracking how different volatiles distributed through the coma. UVS, the ultraviolet spectrograph, would detect emissions from excited atoms and molecules, building on Swift's earlier observations but with far higher spectral resolution. PEP, the particle environment package, would measure the plasma and neutral gas surrounding Atlas, documenting how solar wind interacted with the comet's outgassing. This was data no telescope could provide, measurements that required being there, in space, close enough to sample the environment directly. Between November the 2nd and 25th, JWST would observe whenever geometry and scheduling allowed. The spacecraft had other priorities, other targets in its complex trajectory toward Jupiter. But mission planners had carved out time, recognizing the scientific value of this opportunity. There was just one problem, a problem that would define the next 3 months and test the patience of everyone waiting for answers. The data would not arrive until February 2026. JWST was using its medium-gain antenna for communication. The high-gain antenna, which normally provided high-speed data transmission, was currently oriented to serve as a heat shield, protecting the spacecraft from solar radiation as it maneuvered through the inner solar system. The medium-gain antenna worked, but it drastically reduced bandwidth. Images and spectra got stored on board in solid-state memory. When bandwidth allowed, when other mission priorities were met, the data would be downloaded, processed, calibrated, analyzed, and finally, months after the observations were taken, released to the scientific community. 3 months of latency between observation and knowledge. 3 months where the most detailed post-perihelion data existed but remained inaccessible, locked in a spacecraft's memory, travelling at light speed toward Earth, but not arriving fast enough to satisfy the questions that demanded immediate answers. Did Atlas survive intact? Did it fragment into multiple pieces? Did the chemistry change as perihelion heating drove off the carbon dioxide and exposed water-rich layers beneath? Did the coma expand as predicted? Did anything unexpected happen during those critical hours when the comet was closest to the Sun? The answers existed, right now, captured in photons and electrons, but humans would have to wait. Ground-based observatories picked up Atlas in late November when the solar elongation increased enough that twilight observations became possible. When the comet cleared the worst of the solar glare and emerged into darkness where large aperture telescopes could lock on, the predictions for brightness varied. Some models suggested magnitude 10 or 11, bright enough for 8-inch amateur telescopes under dark skies. Other models were more conservative, predicting magnitude 12 to 13, requiring professional instruments or dedicated amateur setups with long exposures and careful tracking. The actual brightness would tell the story immediately. If Atlas had brightened dramatically, if perihelion triggered a massive outburst or exposed fresh volatiles, the magnitude would be higher than predicted. If it fragmented, the total brightness might increase initially as more surface area became exposed, then drop as fragments dispersed. If it went dormant, if the volatiles exhausted or activity shut down unexpectedly, it would be dimmer than expected. All of that became apparent in the first few nights of renewed observation. The Galileo Project observatories were operational, 3 sites monitoring continuously: Massachusetts, Pennsylvania, Nevada. During November and December, detection thresholds were lowered as Loeb had promised. Any transient object, any unidentified moving target got flagged for analysis. The criteria were specific: objects in unusual orbits, trajectories that did not match catalogued satellites or debris, motion patterns suggesting propulsion rather than ballistic flight, anything that could potentially indicate artificial origin. Loeb had made the timeline public. If probes were deployed at perihelion on October 29th, if they used reverse Oberth maneuvers to insert into Earth orbit, arrival would occur between November 21st and December 5th. The observatories would watch. The probability of detection was low, maybe 10% even if probes were actually deployed, but 10% was better than 0. And if something appeared, if an object showed up that defied natural explanation, everything changed. Every telescope would pivot. Space agencies would mobilize. The conversation would shift from speculation to investigation in an instant. But if nothing appeared, if the window closed without anomalies, the technological hypothesis would lose its last support. The Loeb scale rating would drop. Atlas would be classified definitively as natural, unusual and ancient but natural nonetheless. Europa Clipper, NASA's mission to Jupiter launched earlier in the year, was also positioned for potential observations. The spacecraft was en route, but not yet at Jupiter. Its trajectory would bring it within observation range of Atlas during the post-perihelion period. Coordination between Clipper and JWST was discussed. Both spacecraft had ultraviolet spectrographs. Observing Atlas from 2 different locations simultaneously would provide parallax stereo observations, 3-dimensional information about coma structure that a single spacecraft could not obtain. The geometry was not ideal. Clipper was not optimally positioned. But if the opportunity existed, if mission planners could work it into the schedule without compromising primary objectives, the science would be valuable. The real breakthrough would come from comparing pre-perihelion and post-perihelion states. The August data from JWST showed Atlas before its closest approach. Carbon dioxide dominating at 8:1 over water, coma structure showing spatial variations, ice debris scattered through the outgassing region. The November data from JWST and ground telescopes would show the aftermath. Had the ratio changed? Had perihelion heating driven off the carbon dioxide preferentially, leaving water-rich material exposed? Or had the ratio stayed constant, suggesting homogeneous composition throughout the nucleus? If the ratio changed, it revealed layered structure: carbon dioxide-rich outer shell, water-rich interior. If it stayed constant, the composition was uniform, mixed thoroughly, either from formation or from billions of years of thermal cycling and radiation processing. Both outcomes were scientifically valuable, but they told very different stories about how this object formed and evolved. The chemistry was a record, a timeline written in molecular abundances that could be read if you had the right data. The tail development became another diagnostic. Pre-perihelion images showed faint or absent tail depending on exposure time and instrument sensitivity. Post-perihelion, the tail should be prominent, millions of kilometers long, curved by solar radiation pressure and orbital velocity. Spectroscopy of the tail would reveal what dust grains were being ejected: silicates, organics, ices. The grain size distribution would indicate erosion processes. Small grains meant vigorous sublimation, gas escaping fast enough to lift tiny particles. Large grains meant mechanical disruption, or explosive events, chunks blown off by internal pressure. If Atlas had fragmented, the tail would show complexity. Multiple streams, overlapping structures, each fragment contributing its own tail. Ground-based photometry could potentially resolve individual fragment contributions, map the debris distribution, track how pieces separated over time. Hubble could do this if telescope time became available, though getting directors' discretionary time required justification that the science was urgent and could not wait for the normal proposal cycle. The Vera Rubin Observatory, when it came online, would revolutionize interstellar object studies. The Large Synoptic Survey Telescope would scan the entire visible sky every few nights. Deep exposures, automatic detection of moving objects. Rubin would catch interstellar visitors earlier, when they were still far from the sun and faint. It would track them through perihelion and beyond, build like curves with thousands of data points. The photometry alone would reveal outbursts, fragmentation events, rotation periods, anything that changed the brightness over time. Spectroscopic follow-up with other instruments would be informed by detailed photometry from Rubin's continuous monitoring. Atlas was the prototype, the object teaching us what to expect from future interstellar comets, what their brightening curves looked like, how their activity evolved, what spectral features appeared and when. Every observation of Atlas informed survey design for Rubin, refined detection algorithms, calibrated models. The fourth interstellar object, when it arrived, would be detected faster and characterized better because of lessons learned from Atlas. The November observations also mattered for trajectory refinement. Every position measurement improved the orbital solution, reduced uncertainties, allowed better predictions of where Atlas would be in December, January and beyond. As the comet moved past Venus, past Earth's orbit, heading back toward the asteroid belt, tracking became harder. It dimmed, moved against increasingly crowded star fields. Having precise ephemerides ensured ground telescopes could point accurately. That observing time did not get wasted searching for an object that should be in the field of view, but was not because the coordinates were slightly off. The plasma environment measurements from JWST were unique. No other spacecraft would be close enough to sample the interaction region where solar wind meets cometary outgassing. That boundary, the bow shock, is dynamic, constantly shifting as outgassing rates change and solar wind pressure varies. PEP would measure ion densities, electron temperatures, magnetic field perturbations. All of it feeding into models of how cometary magnetospheres work, how charged particles accelerate, how energy gets deposited into the coma. For Atlas specifically, the plasma data might reveal subtle composition details. Different volatiles ionize at different rates, produce different ion species. The mass spectrometer component of PEP could distinguish between water group ions, carbon dioxide group ions, and others. If unexpected species appeared, molecules that were not detected spectroscopically from Earth, that would be new information. Additional constraints on what was actually present versus what we inferred from remote observations. But all of this remained locked away. JWST had observed. The instruments had recorded data. And now the spacecraft continued its journey, slowly transmitting stored observations back to Earth when bandwidth allowed. Priority went to real-time navigation and engineering data, science data queued for later download. February 2026 felt distant. 3 months is not long in the grand scheme, but it is agonizing when you're waiting for answers to questions that define careers. The wait was necessary. The data would be worth it. Processed, calibrated, analyzed by experts who understood the instruments and knew how to extract signal from noise. When the results were published, they would be definitive. The best post-perihelion characterization of Atlas we could possibly obtain given current technology and mission constraints. Until then, researchers relied on ground observations. Amateur astronomers with backyard telescopes contributed data. The comet was faint, but experienced observers with good equipment under dark skies could capture useful photometry. Each measurement added to the light curve. Each position determination refined the orbit. Professional observatories squeezed Atlas into crowded schedules. A night here, a few hours there. Spectroscopic campaigns organised through international collaboration. Different observatories in different hemispheres taking turns, following the comet as Earth rotated and brought new telescopes into position. Every clear night mattered. Every observation was valuable. And slowly, image by image, spectrum by spectrum, the post-perihelion story came into focus. The comet was behaving. Not fragmenting into chaos, not going dormant and disappearing, just continuing its trajectory, outgassing steadily, following the physics that has governed cometary behaviour for billions of years. But there were hints, subtle features in the light curve that might indicate rotation, periodic variations suggesting that different parts of the nucleus had different reflectivity or activity levels. Nothing definitive yet, but patterns emerging that would become clearer with more data. The tail was there, extended and visible in long exposure images. Not spectacular by historical comet standards, but present. Proof that dust was still being lifted off the surface by outgassing, that solar radiation was pushing it into the familiar streamer shape that gives comets their name. No secondary condensations. No multiple nuclei strung out along the orbit. If fragmentation had occurred, it was subtle. Small pieces that had not yet separated far enough to be resolved individually. Or it had not occurred at all, and Atlas remained intact. The December observations continued the story. Atlas moved farther from the Sun, cooling gradually as solar heating decreased. The outgassing rate should decline, the coma should shrink, the brightness should drop as both the comet and Earth moved farther apart and activity decreased. All of this happened as expected. The light curve followed predicted trends. The spectrum showed the same molecular signatures as before, though fainter as the comet dimmed. Nothing extraordinary. Nothing requiring exotic explanations. The Galileo Project observatories watched through December 5th, the end of Loeb's predicted probe arrival window. They catalogued satellites, tracked known debris, identified transient events that turned out to be asteroids or cosmic ray hits or instrumental artifacts. No unidentified objects appeared in unexpected orbits, no anomalies that could not be explained naturally. The criteria for artificial technosignatures were not met. The probability that probes had been deployed and arrived at Earth dropped towards zero. Loeb acknowledged the null result, posted an update saying the lack of detection did not prove Atlas was natural, only that if probes were released they either missed Earth, arrived outside the predicted window, or were too small and stealthy to detect. The hypothesis remained possible but now lacked supporting evidence. The scientific community moved on. Papers were drafted analysing the chemical composition, the trajectory history, the outgassing behaviour. The data from JWST, from Swift, from Mars orbiters, from ground-based telescopes all went into comprehensive studies that would define our understanding of this object for years to come. Atlas was classified, an interstellar comet from the thick disk, 10 billion years old, unusual carbon dioxide to water ratio reflecting formation in an ancient star system with different chemistry than our own, valuable scientifically, historically significant as only the third confirmed interstellar visitor, but natural, definitely, conclusively natural. The alien mothership hypothesis faded from mainstream discussion. It persisted in conspiracy communities, in YouTube videos, in social media threads where people who wanted to believe found reasons to continue believing. But in scientific journals, in conference presentations, in university classrooms, Atlas was a comet. An extraordinary comet, but a comet nonetheless. February 2026 arrived, bringing the scheduled release of JWST data. The astronomy community prepared. Papers were drafted waiting for new observations, models stood ready to be tested against spacecraft data. When the data arrived, it confirmed what ground telescopes had suggested. Atlas survived perihelion intact. The nucleus remained whole, though the surface had changed. The carbon dioxide to water ratio had shifted, suggesting outer layers rich in carbon dioxide had partially sublimated, exposing water-rich material beneath. The coma showed complexity, jets from active regions, asymmetrically distributed dust grains. Plasma measurements revealed ion species consistent with water, carbon dioxide, and trace molecules. Everything fit the comet model. No anomalies required invoking unknown processes or technology. The JWST images were stunning. high-resolution views of the nucleus showing texture hinting at internal structure, the coma glowing in ultraviolet as molecules fluoresced under solar radiation. These were the best images humanity would capture of Atlas. The comet was moving away, heading into deep space. It would pass Jupiter's orbit in March 2026, receiving slight gravitational deflection, but fundamentally leaving our solar system. By late 2026, Atlas would be beyond Saturn, too faint for most telescopes. By 2027, past Neptune's orbit, visible only through radio astrometry, and then gone. Back into interstellar space, back into darkness between stars, continuing its journey that had lasted 10 billion years and would continue billions more. The story ended not with revelation, but with gradual fading. Atlas slipped into obscurity, remembered in papers and textbooks but no longer visible. What it taught remained. Data archived worldwide, spectra, images, measurements that future researchers could analyze with better tools. Atlas had given us a glimpse of ancient galaxy chemistry, of formation conditions in star systems from when the universe was young. It challenged our models and refined our methods, showed us interstellar visitors come in varieties we had not anticipated, that the galaxy is full of wandering objects, each carrying its own frozen history. And it reminded us how science works, that patience is necessary, that waiting for good data beats speculation, that extraordinary claims require extraordinary evidence, and without that evidence, the simplest explanation is usually correct. Atlas was a comet, ancient, unusual, scientifically valuable, from another star's planetary system. It visited briefly, gave us irreplaceable data, and moved on. We were fortunate to witness it, to have the telescopes, spacecraft, and expertise needed to study it properly, to document this thick disk visitor before it disappeared. The next interstellar object would arrive eventually. Vera Rubin would find it. Telescopes would track it. We would be ready, because Atlas taught us how to look, what to measure, what questions to ask. It was the pathfinder, showing us what was possible when we turned our instruments toward wanderers passing through. The waiting was over, the data had arrived, the story was complete, and Atlas, ancient and cold, continued its endless journey through the galaxy.